Well, thank you, Rusty and Denisha, for putting this whole thing. And I would like to extend my thanks to the entire ACI staff that put that ACI Excellence Award program together. It's humbling and gratifying to be part of it. We started placing our project in this program since the inception. We already won 4 times high-rise category, second place, yet to win the first place. But it's a great thing about this award. It's actually an international award. When you come to these presentations, as we can see here, you have people from all over the world bringing these beautiful projects. As we saw last night, all these entries were amazing and a lot of hard work. Every project is touched by 1,000 people or more by the time you design it, construct it, build it, and it changes the landscape of cities, for that matter, and touch us in so many ways. So the Ayer is a long history. It's in Seattle. If people don't know, Seattle is a high seismic region. There's a subduction plate moving. A lot of attention is given to earthquakes. High-rise buildings are particularly complex structure to design in the high seismic areas. The Ayer in particular is a 45-story tower, 5 levels below grade, multi-family high-end luxury condominium in the Denny Triangle, which is kind of ties in downtown. It's a vibrant neighborhood of Seattle that ties in downtown with South Lake Union, if you guys have been to Seattle. And we had to pay critical attention to cost. It's a private-driven project, and to speed, because schedule, cost, all these things come together to make these projects happen. So just a quick overview. It's 454 units. It's about 600,000 square feet, 6 levels below grade, and of parking, and then 3 levels above grade was parking. Beautiful lobby area was amenity that ties in the corner of that street. Many thanks to the developer Holland Partner Group. The good thing about them, they're also the general contractor. Holland Construction will also thank the concrete contractor, which is Conco Concrete, and Robert Thompson was the architect. If you could see, look at the building, the way it's been designed, it actually was inspired by the Pacific Northwest, where you have these jagged sides. This is actually the tectonic plates, quote unquote, per the architect, that kind of shows that facade that goes in and out, which created some challenges for us on a structural standpoint, because we had to create these long cantilevers without moving columns. Quick thing on the structural overview of the building, has a lot of great things and innovations and buildable details throughout. So we use 8-inch post-tension slabs. We have spans about 29 to 30 feet and cantilevers up to 12 feet without any drop heads. We use high-strength column up to 15,000 PSI. That was a bit challenging because the entire building will also use one of the first buildings that used Type 1L cement in the US of that size to reduce carbon footprint. We're also on the walls. So the lateral system of the building is actually not allowed by the prescriptive language of the code, so we have to do performance-based design. So we have to analyze the building with this core, and we'll put fiber link beams that are not part of the code, but you can do it if you do nonlinear analysis and show that the performance of that core would work nicely. It takes a lot of energy. You put 11 pairs of ground motion. Each one is about a minute long, and every 0.05 seconds, you check the stresses on the building as the 11 pairs moves that model. So it takes a lot of iteration, a lot of back and forth. One of the things we wanted to do is we had 16 columns. We worked hard and fought hard and negotiated location with the architect and the ownership so we don't have to add any transfer beams. Buildings this size, a transfer beam would be a floor height and would slow down construction and would disrupt the behavior of the lateral system. So here's a model. This is out of Revit, which is Visicon 2, but you can see here the middle, the red is the core, going concentric core from the foundations, the foundation mat, all the way to the roof. You have 16 columns around. We created some crafty, you can see here, jogging and walking of columns. Some of them walked in 3 different directions, just so that we don't put any transfer beams. So we didn't have any transfer beams at all from dynamic base. We call it dynamic base, which is grade level all the way to the top, which made the things much easier, less congestion, and eliminated all the transfer beam that could impair some of the occupancy of floors. One of the cool things we did, and this is supposed to be a video, maybe the next click should do it, is because we had a high strength, you can see here, this is the column, and the column was 15,000 PSI concrete, and the slab was 6,000 PSI concrete. So we don't have, the code requires you to do puddling. I don't know if you guys know puddling. You basically take another mix of concrete, you put it on top of the column, intermix, and then because you don't have so much differential between the slab mix and the column mix, add the column slab sandwich, which is right here. I'm going to click to see if that video will work. Oh, yeah, it does. So these are the stud rails. This is a rebar. And the way we do that, these are the shear bars that we put into. The green is the PT cables. You can see them here, too. And then this is the top reinforcement. And then you put this stay form. And then when they pour the slab and they stress it, you have this little hole because that stay form keeps the core of the column without being poured. But it does not slow construction because you pour the slab, you stress, you have this little cavity over the column. The next day they come and pour the column, and the concrete mix of the column goes into that cavity. It's pretty cool, slick trick. I'm gonna replay it again, see if that works. So you can see it again, and then avoids the puddling. The trick was usually to put the stay foam, but what they did here, they put that stay foam first. You have to make sure you put the shear steel bars so that on top of the friction between the concrete, you have shear steel that passes through. It's like a midpoint bar that goes into that joint. And then they put stay foam again up here after they put the top bars, and they pour it. Much easier than putting two mixes, try to intermix them, so on and so forth. So that was a big thing on constructability and buildability. The other cool thing on that job is we used actually fibers link beam. High dosage of fiber, you could see it, and instead of using the diagonal reinforcement in these beams because they are taxed by a lot of shear, and a regular beam does not work. So what we did here, we put basically that piece of concrete between the two walls. So this is a boundary element of the wall, and this is the other boundary. Between the two walls, we put a special mix with high fibers. It's about 160 pounds of fiber per cubic yard. It's a very healthy fiber dosage, to 200, depending what we need. But what happens is you reduce the rebar in that beam by about 40% from a typical beam. So it's much easier to place. You don't have the diagonal that clashes with the top rebar coming down. So it turns out to be a very constructible tool that streamlines the rebar of the core going up the building. And the neat thing about it, a lot of times you can pour this after the fact. What they do is they pump the wall with concrete, they bucket this with a steep bucket with fiber concrete, they vibrate it, and they put stay foam, and they keep on going with the building. Here's a video showing how that fiber concrete is putting in. It's interesting, we use the SCC mix. When you put the fibers, not because the fibers suck, steel fibers, they don't suck water, but it turns the SCC mix to a 6-inch slump. You have a 27-inch slump for a self-consolidated mix, and you put these fibers in, suddenly you're down to 6 inches, plus or minus. So, but they all over the mix, you don't see them when you strip, so it's a pretty neat thing. We've done about 15 buildings like this throughout. Now, the underground, the below-grade construction was really interesting. First of all, we start with the mat. We had a lot of cool concrete specification for different concrete mixture for the building, but the mat is basically about 10 feet thick to plus. 10, around the elevator pit is about 15, but basically most of it is about 10 foot thick. And they did a single pour for the entire mat, about 5,000 yards. So basically, they start at night, they finish in the morning, about 12, 14-hour pour. You have trucks coming in. So think about it, 10 feet of concrete, it's mass concrete. There's a high heat of hydration, so we always make sure that the cement content of these mixes is less than 450 pounds, and we kind of extend the strengths, so you don't need that strength till about 90 days or 120 days to make it easy on the ready-mix guys to bring those mixes to us. If you pour that mix like a regular 6,000 mix with 600-pound cement, you won't be able to walk on it in 2 days. It's going to be very hot. So that's one. Two is we cover it so we keep the heat differential the same between the center and the top of the mat for a few days till things come down. We'll look at the temperature gauges for that. The other cool thing is It's a pencil tower in the downtown, so it's 120 feet by 100 plus feet, 110 feet. So you want to go fast, and the basement wall creates a trouble because if you have to pour the basement wall, pour the slab, pour the core, you'll be stuck in that hole 6 levels below grade for several months. One job we did, they were in the hole. They came to go down and up. Took them a year. So what we do is this is actually the shoring system. That's not concrete. We allow them to put the slabs against the shoring system, and then what they do is they detension. There's tiebacks on the shoring system. They detention it. Now the slab becomes bracing the shoring system, not the tiebacks. You don't have to do blockouts in the basement wall. And then you don't do the basement wall till later. So these are formwork put at the joint of the basement walls. You have a basement wall above, basement wall below, slab in. And what they do is they come back later when the tower is up to level 2. They come back and shoot with shotcrete the basement walls. And they're pretty thick basement walls, 16 inches. And then, so embodied carbon was an interesting thing on this. Let me just go back here too. One of the things we used is we used grade 80 steel throughout the foundation, grade 80 steel throughout the boundary elements of the core walls because there's a lot of tension involved. And then we used the confining steel, was grade 80 steel, to reduce the amount of confinement. The other thing we did is we created these column cages to lift, so you reduce the amount of times you put these columns on site. So that if you have 16 columns, what they did, they staggered the columns. It's a cage that goes 2 levels. So some of the columns, you only have to place half of the column every cycle of floors because the other one is already sticking up. We do it the next one. So it's 2-story lifts. And that works really nicely and speeds up the floor cycles by quite a bit on the typical floors above in the building. The carbon was interesting because by just using Type 1L cement, we were able to reduce about 10%. So this is about equivalent, we did the math on it, about 450 tons of CO2 reduced just right off the bat. And then being efficient and putting transfer beam and all that stuff, people don't realize a lot of the carbon reduction is the big question. And I always ask myself, it's like, you see all these highways, a lot of these bridges, but you can easily reduce carbon by making your design a bit more efficient by at least 10%. You always can make your design a bit efficient. So that was a big thing. And then, so high strength bars also reduce the embodied carbon. Now, depending how steel is being made, either from iron ore or recycled steel, most of the stuff we use in the Northwest is recyclable steel, so there isn't a lot of CO2, but there's still some, because you have to heat it, melt it, and transport it. So by using high-strength steel, you reduce the amount of rebar you use, and then therefore that helps with the carbon footprint. So the project here did it great. We won a couple of years ago the NAIOP High-Rise Residential Development of the Year in 2024. Last week, we won the NCSCA, which is the National Council of Structural Engineering Associates. It was a summit in New York. We won the Outstanding Multifamily High-Rise Project category for 2025, and a few other awards and publications. And then CRSI Award right here in 2024. And yesterday, we won the ACI Excellence Award, second place, but we're working on the first place. And yeah, so basically, conclusions, we are advancing material. We use innovative material like fiber link beams, fiber and concrete, leading edge constructability. I showed you that detail. And all of it happened was a collaboration with the concrete subs and the ready-mix guys. We sit down with them early on, and we try to make them comfortable with the ready mixes. Otherwise, they get freaked out when they see a 15,000 PSI mix. And I think that's it. Any questions?